Hello, my name is Adrian Boico and I will be presenting our paper, Self-Improving SLAM in Dynamic Environments, Learning When to Mask. The context of our research is dynamic SLAM. SLAM meaning simultaneous localization mapping in a static environment. Of course, the real world is not static, it is dynamic, which is why SLAM has been extended to dynamic environments and is known as dynamic SLAM. Dynamic SLAM has many applications and some include autonomous vehicles, robotics, augmented reality. The general principle of a SLAM is to take as input video frames and output camera trajectory and a map. Firstly, we have basic SLAMs. Those don't mask any object. This means that they may drift in case dynamic objects are tracked. On the other hand, we have dynamic SLAM with full masking. This means that the SLAM will mask all supposedly dynamic objects like people or cars. As a benefit, we won't have the drift that appears in basic SLAMs. However, if they mask too many objects, they may fail early due to lack of features. Finally, there's our approach, dynamic SLAM with temporal masking. We propose here to mask objects exactly when appropriate, when we predict that masking them improves SLAM performance without any kind of geometric priors. This means that we won't have neither drifts nor early failures due to excessive masking. We already know how to mask objects. There are many approaches in the state-of-the-art to do so. The question now is when to mask these objects. So we propose SLAM with temporal masking. Temporal masking is a new paradigm to decide when to mask certain classes of objects. First, we propose the temporal masking network, which is a network that learns temporal masking decisions to mask or not a certain class. Then we propose a method to achieve automatic dataset annotation, since we need to train our networks at a low cost, meaning that we can use self-supervision. Our approach in general consists in a layer on top of existing dynamic SLAMs. Dynamic SLAMs typically consisting from input frames, key point detection, key point filtering, then tracking and mapping. In our case, we use temporal masking to infer frame by frame which classes have to be masked. So our approach works as a binary trigger on the key point filtering step, meaning that if our network infers that a certain class has to be masked, then we segment all objects of this class and input this mask in the key point filtering step, altering it. Finally, we also propose the conceived dataset, which is a dataset including sequences in dynamic settings of controlled difficulty, and a unified SLAM metric, which is a metric very practical for training purposes and for dynamic SLAM benchmarking. A temporal masking network first consists in inputting video samples, meaning a set of past frames plus the current frame. Note that the past frames do not need to be consecutive. The temporal masking network first consists in computing features using, for instance, ResNet50, then an LSTM, then fully connected layers. This means that our network is memory-based. We can use information that is far in the past to make a decision to mask or not to mask a certain class, if the decision is yes. In this case, we will compute the segmentation mask of this class for this frame, which we will then input in the key point filtering step. In the case the decision is no, then we do not need to mask anything. We simply use the image as is without filtering any key points. Note that here the source of semantic mask is arbitrary and the same as the one that is used during the annotation step. Automatic dataset annotation consists in 3 steps. First, we sample temporal masks uniformly. This means that we create sets of masking decisions, deciding for every frame and every class when to mask objects of this class. Note that the semantic mask generation program is arbitrary and given by the user, as well as the SLAM algorithm and the sequence. We will not go into details here, but the general idea is that the space of all temporal masks can be represented as a constrained binary tree, where a temporal mask is a root to leaf path. However, computing the whole tree is computationally intractable, as the tree size grows exponentially with sequence length. So we developed a closed form expression that gives the exact size of any subtree. This means that at every bifurcation, we sample RIO between 0 and 1, then pick the appropriate path according to the relative size of the subtrees under the branches. We prove that this process keeps the sampling process uniform. The second step is to benchmark all temporal masks to evaluate their effect on SLAM performance. Finally, we aggregate all sampled masks according to their performance, which results in a real value-add vector that is threshold to finally obtain a temporal mask that maximizes performance for the given semantic mask generator. We will now see some qualitative results on common datasets on our own dataset. On the left, you have the baselines. On the top left, basic SLAM, meaning no masking at all. On the bottom left, you have dynamic SLAM with full masking, meaning that dynamic objects are masked all the time. Finally, on the top right, you have our approach, dynamic SLAM with temporal masking. Here we are evaluating a Kitty sequence. Note that the Kitty dataset is fairly easy from a dynamic SLAM point of view, meaning that most times masking or not dynamic objects has no effect at all on the final performance, which is why we can see some objects which are alternatively masked or not masked. That said, with slightly better choices regarding masking, we can still get a minor improvement on the final performance. We can see here, for instance, when there are vehicles that are parking, that they are masked while they are parking and not masked when we are very far or when they are out of view. We have now a fairly simple example of term RGBD. Here, the solution is to mask objects, meaning here people, all the time, since they are moving all the time. And our approach is able to understand this, so it works. Now, if you look at the no masking approach, you will see that it tracks points on people, which causes the drifting and a very poor final performance. We now have a more complex example on the outdoor subset of our conceived dataset. Here the person is moving but not the car. So the solution here is to mask only the person when it's moving and not the car. And actually, nor the basic SLAM nor the dynamic SLAM with full masking are able to do this, which is why we can see that there are points that are tracked on the person, meaning the basic SLAM will drift, and the full mask will lose tracking when it gets too close to the car, since it removes its only source of features. And finally, we can see that the only approach that truly works is ours, since it's able to differentiate between both situations. We have one last example on an indoor sequence of our dataset. Here the object is pulled to the left, and we can see that there are many points that appear on the object if it's not masked, meaning that the basic SLAM does not work at all. On the other hand, the full masks and our own approach mask the object when it's moving, so it will prevent any kind of drifting and achieve good performance. We evaluated various algorithms, the state of the art, and there are two conclusions. First, there are apparently contradictory results regarding the AT-RMSE, the trajectory accuracy, and the tracking rate, which is the ratio of tracked frames, as you can see in the red box. It appears that not masking objects ensures long tracking but poor accuracy, while masking too many objects ensures good accuracy but early failures, meaning a low tracking rate. For this reason, we use the unified SLAM metric here, although it was initially developed for the benchmarking step of our automatic dataset annotation method. Secondly, the overall result is that our approach overcomes the state of the art. The main reason is that the memory-based approach gives a long-term analysis capability, unlike current approaches that analyze object motion over the latest frames. This means that our network can understand complex ideas, like an object that moved 100 frames ago is likely to move again on lowest SLAM performance, even if it's not moving at the moment. In other words, our approach is more about estimating the likelihood of an object causing problems to the SLAM. Note that the fact that dynamic objects are masked is a result of the learning process, not something that we assume. We do not make any assumption on motion. In conclusion, our main contribution is the temporal masking paradigm and a viable implementation of it, with the temporal masking network, a memory-based network to learn temporal masks, and a method to automatically annotate sequences with masking decisions for self-supervised training, in addition to the unified SLAM metric and the consim dataset. The result is that the proposed approach overcomes the limits of current dynamic SLAM algorithms on real data with no geometric priors like object motion. Thank you for your attention, and I hope to meet you at BNVC 2022.